These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm. Or you can just use the link in the info box. Thank you. Okay, well, let's give this a shot. How would you get started with this?
Okay. So it says find the magnitude and direction of the electric field. So if it's charge per unit length, you know that it's the charge is linear, basically. So you know that the electric field is coming up radially in all directions, so we should choose a cylinder for the Gaussian surface.
Good, good.
So big R is the radius of our charged surface. So we want to draw a Gaussian surface inside of that.
Okay, well, let's try to work this out on paper. You should probably get a blank piece of paper because this will be complicated.
So in this one we'll have radius little r.
Good.
Okay, so now we know that so the electric field is E times the area of the surface that we chose. So it's
Good.
the area of the cylinder.
Good.
So it's E times area, and that's equal to Q enclosed over E naught. And we know that the area is 2 pi little r times length.
Okay, what is going to be the direction of the electric field vectors? I think you already mentioned what direction will they be in?
Radial.
Yeah, so the electric field vectors are all going to be pointing, say, like this, away from the center. So we know that they're all going to be perpendicular to the sides of this cylinder. So we don't need to break the electric field into components or anything here. There will also be a flux, there won't be any flux through the sides of the cylinder because the electric field will be parallel to the sides of the cylinder. So the only flux will be the top and the bottom of the cylinder, whatever you call it. So the only flux will be through this surface and this surface. So we can just simplify.
Why is that?
Well, we know that the electric field lines look like this.
Yeah.
Now remember what we're trying to figure out is
Oh,
the
I
electric
see.
flux.
I get it. I get what you're saying.
Well, the electric flux only depends on the components of the electric field that are perpendicular to the surfaces. Well, there's no flux through this right-hand end because the electric field lines are just skimming parallel to this. The only flux, and the same for this left end, the only flux is from the electric field lines that are penetrating perpendicular to the top or to the bottom of the cylinder. So as is usually the case, we don't need to bother breaking these electric fields into components. We can just use the actual level of the electric field here. This is only supposed to have the component of the electric field that is actually penetrating perpendicular to the surface, but that's going to be 0 for here, 0 for here, and for the top and the bottom it'll just be the same as the electric field. Okay. That's one reason why this is a good symmetrical Gaussian surface to draw, this cylinder. So you were right that we have E times A. So I fell a little bit behind you. What have you plugged in here so far?
2 pi RL.
So we need to figure out the lateral surface of the cylinder. And what are we using for L? That must be the length of the Gaussian surface that you drew. All right, so it's good that you've learned that this is the surface area, the lateral surface area of a cylinder. It's the circumference times its length. All right, so the lateral surface area, we don't need the area of the left and the right-hand side because there's no flux through there, but the area of the top and the bottom of the cylinder would be 2 pi r times L, so that's good. Okay, good.
And then for Q enclosed,
Right.
so we know that it has uniform charge per unit length lambda.
Right.
So that's the charge density. So I think it would be lambda times L.
Mm-hmm.
I think it would be lambda times L, except that the only thing I'm confused about is that I don't think that takes into account the third dimension of it, because it's a volume of charge, I think.
Let's see. Okay. Yeah. So what are the units for lambda? Well, we know that lambda is charge per meters. Coulombs per meter. And we're trying to figure out the total number of coulombs. So it makes sense that we should be multiplying by the total number of meters. And that here would be L. You just invented this symbol L for the length of your Gaussian surface. And that'll give us Q coulombs. So this really is correct. Now, in this particular case, it's true that this is three-dimensional, but that's all the information we need is already built into this lambda. So this is already saying that if you take 1 meter of this cylinder, there will be a total charge of lambda coulombs in the whole three-dimensional shape represented by that 1 meter. So this is, even though this is only telling us the coulombs in 1 meter, it's not just telling us, say, the coulombs that's linear like this. It's telling us the entire amount of coulombs in the entire 1 meter of cylinder. I don't know if that made any sense. But we do have a problem here, which is this tells us the total amount of charge in the entire 1 meter of cylinder, but our Gaussian surface is inside of the cylinder, and we only want part of that charge.
Yeah.
So what we're going to have to do is, so we could say, if we did have, in this L meters of cylinder, there really will be lambda times L units of charge in the entire L meters of cylinder,
Yeah.
but we need to figure out how much is enclosed in this little cylinder of this radius. We've done 1 or 2 problems like that, where we have to go from the total amount of charge to a portion of the charge, but that gives people trouble a lot. Do you have any idea how we could work that out mathematically?
I think we would do a ratio
Yeah,
of little r to big R.
good.
But I'm not quite sure what that would look like.
All right, I'm not sure if I'm quite sure myself, so let's see if we can work it out together.
Okay.
So let's start by thinking about what would happen if we were focusing on the entire radius of big R. Well, in that entire radius of big R, we just figured out that this would be the total amount of charge in that radius. Now, what does the total amount of charge depend on? The total amount of charge doesn't depend on the radius that we're focusing on or on the area that we're focusing on. It depends on the volume that we're focusing on. So we'd have to figure out what would be the total volume if we were focusing on the entire capital R radius.